Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on cooling towers and cooling water system in plants which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to list and describe the basic components of a cooling tower. Describe the principles of heat transfer in a cooling tower system. Describe the relationship between heat exchangers and a cooling tower. Explain how an atmospheric cooling tower operates. Explain how a natural draft cooling tower operates. Explain how a forced draft cooling tower operates. Explain how an induced draft cooling tower operates. Illustrate crossflow and counterflow in a cooling tower. Describe a water cooling system. Describe the characteristics of water that cause problems with water cooling systems. Before starting the course, let us have a look at key terms. Air intake louvers are slats located at the bottom or sides of a cooling tower to direct airflow. Approach to tower is the temperature difference between the water leaving a cooling tower and the wet bulb temperature of the air entering the tower. Basin is concrete storage compartment or catch basin located at the bottom of the cooling tower. Basin heaters are designed to keep cooling system water from freezing during the winter months. Biocides and algicides prevent biological growths from interfering with water circulation. Blowdown is a process of controlling the level of suspended solids in a cooling tower by removing a certain amount of water from the basin and replacing it with makeup water. Capacity is the amount of water a cooling tower can cool. Cell is the smallest subdivision of a cooling tower that can function as an independent unit. Some cooling tower systems have multiple cells. Cooling range is the temperature difference between the hot and cold water in a cooling tower. Cooling towers are evaporative coolers specifically designed to cool water or other mediums to the ambient wet bulb air temperature. Cooling tower types are typically classified as induced, requires fan, forced, requires fan, atmospheric, and natural draft. Drift eliminators are devices used in a cooling tower to keep water from blowing out. Drift loss is entrained water lost from a cooling tower in the exiting air, also called windage loss. Dry bulb temperature, DBT, is the air temperature as measured without taking relative humidity into account. Evaporate is to turn to vapor. Evaporation removes heat energy from hot water. Fill is plastic or wood surfaces that direct airflow and provide for contact of water and air in a cooling tower. See also splash bar. Forced draft is type of mechanical draft cooling tower that uses fans to push air into the tower. Induced draft is type of mechanical draft cooling tower that uses fans to pull air out of the tower. Leaching is the loss of wood preservative chemicals in the supporting structure of the cooling tower as water washes or flows over the exposed components. Parts per million is 1 ppm equals 1 pound to every 1 million pounds. Typically associated with suspended solids in the basin or product stream. Plenum is the open area sandwiched between the fill in the center of an induced draft cooling tower. Psychrometry is the study of cooling by evaporation. Relative humidity is a measurement of how much water air has absorbed at a given temperature. Scale is the result of suspended solids adhering to internal surfaces of equipment in the form of deposits. Splash bar is a device used in a cooling tower to direct the flow of falling water and increase surface area for air-water contact. Total dissolved solids, TDS, are the dissolved minerals, such as magnesium and calcium, found in water, which is typically treated with sulfuric acid. Water distribution header is a pipe that evenly disperses hot water over the fill of a cooling tower. Water distribution system is typically consisting of a deep pan with holes equipped with nozzles that distribute the water across the fill using gravity. Some systems utilize a pipe and spray nozzle design. Wet bulb temperature, WBT, is the air temperature as measured by a thermometer that takes into account the relative humidity. Windage or drift loss is small water droplets that are carried out of the cooling tower by flowing air. Cooling tower applications and theory of operation. Cooling towers, as shown in picture, are heat transfer devices designed to cool water for reuse. They cool hot water by bringing it into direct contact with air, using countercurrent or crossflow patterns. A cooling tower contains wood or plastic slats, called fill, that direct airflow and the flow of water falling from the top of the tower. The downward flowing water coats the fill and forms a film, thereby increasing the surface area for contact between the cool air and hot water. Hot water transfers heat to the cooler air it contacts in the tower. This process results in both sensible heat loss and evaporation. Sensible heat is heat that can be measured or felt. When water changes to vapor, the vapor takes heat energy with it, leaving behind the cooler liquid. Evaporation, which accounts for 80 to 90% of the heat loss, is the most critical factor in cooling tower efficiency. It is affected by relative humidity, that is the amount of water in a given quantity of air at a given temperature, wind velocity, and temperature. Other factors that affect cooling tower efficiency are tower design, water contamination, and equipment problems. Cooling towers can be described as psychrometry devices. Psychrometry is the study of cooling by evaporation. Temperatures in a cooling tower are closely controlled. The temperature difference, delta T, between the inlet air temperature, wet bulb, and the outlet water temperature is referred to as the approach to tower. The temperature difference between the hot and cold water is referred to as the cooling range. Cooling tower capacity is defined as the amount of water a cooling tower can cool. There are two ways to measure temperature: dry bulb temperature, dBT, and wet bulb temperature, WBT. Wet bulb temperature takes into account the relative humidity, whereas dry bulb temperature does not. Wet bulb temperatures usually are lower than dry bulb temperatures. The wet bulb temperature, perhaps the single most important factor in cooling tower performance, can be described in several ways. The lowest theoretical temperature to which water can be cooled in the tower. The temperature of the air saturated with water, also referred to as the dew point of air. A theoretical temperature that cannot be reached, only approached. Basic components of a cooling tower. Most modern cooling towers are built with treated wood, cedar, cypress, redwood, or plastic because these materials are resistant to the negative effects of water. As hot process water returns to the tower, it enters the water distribution header, which is a pipe located at the top of most towers as shown in picture. From here, water is sprayed or allowed to fall down into the tower over the splash bars and fill. The splash bars direct the downward flow of water and increase the surface area available for air-water contact. The material inside a tower that directs the flow of water and air is called the fill. Fill can be arranged in patterns that produce either counterflow or crossflow. Pumps suction water from the water basin and discharge it into the cooling water supply header. The supply header distributes water to process exchangers, where it absorbs heat and returns to the top of the cooling tower through the cooling water return header. Most towers develop significant draft or air movement due to design or air density differences. Drift eliminators prevent water from being blown or sucked out of the tower. This type of water loss is called drift loss or windage loss. Makeup water is added to replace water that has been lost by evaporation or blowdown. Induced draft cooling towers use fans to pull air out of the system. Forced draft cooling towers use fans to push air into the system. Some cooling towers have air intake louvers, slats located on the side of the tower to direct airflow. These louvers can be fixed or movable depending on the tower design. A hyperbolic, that is chimney, tower has a stack above the fill and water distribution system. Cooling tower classification. Cooling towers are classified by how they produce airflow and the direction the airflow takes in relation to the downward flow of water. Airflow is produced atmospherically, naturally, or mechanically. Atmospheric and natural draft cooling towers do not use fans to produce airflow. In an atmospheric cooling tower, wind velocity activates the heat transfer process. In a natural draft cooling tower, temperature differences inside and outside the tower change the density of the air. Water vapor and air rise naturally up the chimney. Atmospheric towers initially have a cross-flow airflow, whereas natural draft cooling towers can be arranged with cross-flow or counterflow fill patterns. Induced draft and forced draft cooling towers use fans to move air into and out of their systems. Although mechanical fans use energy, heat transfer rates are much higher when these devices are used. Forced draft cooling towers primarily use counterflow arrangements. Induced draft cooling towers primarily use crossflow, but counterflow designs are available. The world's tallest cooling tower is Germany's Niederaussem power station, standing 200 meters or 656 feet. Wet cooling towers operate using the scientific principle of evaporation. Examples of wet cooling towers include 1. Induced draft crossflow, 2. Forced draft counterflow, 3. Atmospheric, and 4. Hyperbolic or chimney. Dry cooling towers operate using the scientific principle of convection by heat transmission through pipes or tubes or surfaces that separate the working fluid from the ambient air. Hybrid wet and dry cooling towers can be found in operation at many systems in the chemical processing industry. Atmospheric cooling tower. In atmospheric towers, as shown in picture, wind moves air into and out of the tower. Airflow rates are determined by wind velocity. The tower is designed so that winds blow in horizontally, so the air moves in a crossflow direction. Cool air enters the tower through the louvered sides and passes across the downward flowing hot water. As the air becomes heated by contact with the hot water, it travels up because hot air rises. This air is moving in a counterflow direction, opposite the direction of the falling water. The top of an atmospheric tower has drift eliminators to stop water loss when wind velocity surges. The location of an atmospheric tower is important because wind velocities of 4.5 to 6.5 miles per hour are required in order for it to function properly. These towers are designed for water leaving the tower to be 4 degrees Fahrenheit or 5 degrees Fahrenheit or 215.55 degrees Celsius lower than the wet bulb temperature of entering air. Atmospheric cooling towers have a 30 to 55% efficiency rating for cooling water. Because this system does not require a fan, it is very cost-effective. However, its efficiency can fluctuate greatly because it depends on an uncontrollable factor, wind velocity. Heat transfer drops significantly with the loss of airflow. Natural draft cooling tower. Hyperbolic or chimney towers are natural draft towers that have a large stack or chimney as shown in picture. They usually are associated with power plant operation. Commercial towers are typically around 310 feet high with a lower diameter of 210 feet and a throat around 120 feet that gradually widens to 134 feet at the top. They are designed for flows in excess of 500,000 GPM, gallons per minute. Airflow is produced by temperature-induced density differences inside and outside the stack. Hyperbolic towers can have fill patterns that are either crossflow or counterflow. Airflow rates are higher in a crossflow tower, but evaporative heat transfer is more efficient in a counterflow tower. The fill and water distribution system are located below the chimney or stack. Hot water is pumped to a distribution system that is much lower than would be found in an atmospheric tower. During operation, a natural draft tower resembles a large smokestack. Air enters the cooling tower at the base and is directed into the internal fill pattern. As hot water drops through the fill, it is exposed to the cooler air. Density changes inside the chimney create the required upward draft. Heat is removed through the chimney. Natural draft efficiency is linked to the relative humidity and the temperature of the outside air. Forced draft cooling tower. Forced draft cooling towers force air in mechanically by the use of fans as shown in picture on the lower side of the tower. Forced draft towers usually have solid sides without louvers. The fans push in 100% of the process air. Flow direction is counterflow, the fans push air upward against the downward flow of water. Air and forced draft towers can have high velocities, but the exiting air slows so much that it is recirculated back into the tower, cutting efficiency by 20%. Forced draft cooling towers have much higher heat transfer rates than atmospheric and natural draft cooling towers, and they are significantly lower in height. This type of cooling tower is less efficient than induced draft towers because some hot air is recirculated. Induced draft cooling tower. An induced draft tower is another kind of cooling tower that produces airflow mechanically as shown in picture. It differs from the forced draft cooling tower in that it pulls air out of the tower rather than forcing it in. Airflow in an induced draft tower is slower than in a forced draft tower, but heat transfer through evaporation is more efficient. The tower fan, located on top of the tower as shown in pictures, produces discharge rate strong enough to lift the hot air above the tower, so hot air is not recirculated into the tower. Induced draft towers can circulate airflow horizontally, crossflow, or vertically, counterflow. During crossflow operation, drift eliminators are located in the center of the tower to reduce water loss. Counterflow operations force air vertically across a solid area of fill, and drift eliminators are located above the fill and water distribution headers. Water cooling system. In the manufacturing environment, heat exchangers and cooling towers work hand in hand to create a water cooling system. As cool water is pumped from the tower to a heat exchanger, the hotter process fluid transfers heat to the cooling water. The water, in turn, removes heat from the process fluid. The process flow continues on to the next step, whereas the hot water is returned to the tower to be cooled. A centrifugal pump sends the hot water to the top of the tower, where it enters the water distribution header. The hot water is distributed evenly throughout the tower, where much of the heat it had gained is given up in evaporation. The cooled liquid is recirculated back to the heat exchanger and the process loop continues. Heat exchangers can be connected to cooling towers in a variety of ways. The two most common are parallel and series as shown in picture. In parallel flow, the process flow goes through multiple exchangers at the same time. In series flow, the flow passes through one exchanger before it goes to another. The trouble with water. Over time, water dissolves everything it touches. The Grand Canyon is strong evidence that water can remove large and small obstacles. Hot water dissolves solids faster than cold water. Hot water dissolves a little bit of everything it comes into contact with. By the time the hot water returns to the tower, it is full of suspended solids. Hot water also has a tendency to become corrosive and to form deposits. When hot water enters the cooling tower laced with suspended solids, it undergoes evaporation. This process removes water and leaves the solids. The remaining fluid concentrates in the basin. Over time, this concentration builds up to levels that must be controlled. The materials used to construct a cooling tower must be durable and capable of withstanding wide temperature differences. Treated wood, cedar, cypress, redwood, and plastic usually are used as construction materials. Wood is able to handle the temperature variations experienced in a cooling tower. Operators face the following problems when working on a cooling tower system. Suspended solids can accumulate in the water and eventually form deposits or scale. Electrochemical reactions with metal surfaces cause corrosion. Silt, debris, and algae foul and plug exchanger tubes. Fungi and bacteria cause wood decay. There are several approaches for solving each of these problems. Operators check the level of suspended solids frequently. The level of suspended particles is measured in parts per million, ppm, that is 1 ppm equals 1 pound, to every 1 million pounds. The level of suspended solids is then compared against an acceptable standard. The ratio of the actual to the standard level is called the cycle of concentration. The problem of suspended solids is controlled by a process called blowdown. A certain amount of water is removed from the system and replaced with fresh makeup water. Scale-forming solids can be removed with softening agents, or suspension of solids can be prevented by adding chemicals. Another approach is to precipitate the scale so it can be removed. To precipitate is to get particles to fall from suspension. Corrosion can be minimized by the addition of chemical inhibitors, which form a film that protects metal. Fouling can be controlled by filtering devices, alone or with dispersants that prevent suspended solids from accumulating. Biocides, such as chlorine or bromine, can be used to prevent wood decay. Another problem found in cooling tower operation is leaching. Leaching is the loss of wood preservative chemicals in the supporting structure of the cooling tower as water washes or flows over the exposed components. All of these problems and solutions require monitoring. Operators are responsible for testing and checking pH of water, total dissolved solids, TDS, inhibitor concentration, chlorine or bromine concentration, precipitant concentrations, tower equipment checklists, filters and screens, wet bulb temperature and humidity. Cooling tower system. Cooling tower 302 is classified as an induced draft, or draw-through, cross-flow, single-cell device that is primarily designed to control the temperature on condenser X204. A cooling tower is often referred to as a heat rejection device designed to extract excess heat from the returning water and expel it into the atmosphere. This picture shows what the cooling tower system looks like. This type of heat transfer relies on the principle of evaporation. When this process occurs, heat from the water is absorbed by the airstream that raises the relative humidity to near 100%. These heated currents are quickly dissipated by the wind. Cooling tower 302 is an evaporative heat rejection device that can significantly reduce water temperatures. Cooling tower 302. CTW302 is an enclosed structure with a system of air louvers designed to direct airflow across the fill. As warm water enters the top of the cooling tower, the water distribution system carefully sprays or directs fluid flow over a labyrinth-like honeycomb, splashboards, or fill. The purpose of the fill is to allow the hot water to spread out over the surface of the boards. The fill provides a vastly expanded surface area interface that enhances air-liquid contact. As evaporation occurs, the air becomes saturated with water and is carried out of the cooling tower system. CTW302 uses a fan to draw air into and across the fill. The fan is located on the top of the cooling tower and slowly draws air into the system and rapidly discharges it at the exit point. The cooled water continues to drop through and over the fill until it enters the basin. A typical cooling tower is a heat transfer device designed to cool water so it can be reused in industrial applications. The safety aspects of the cooling tower system include the following areas: hazardous energy, chemical additives, see the sections Chemical List and MSDS, rotating equipment, hazards of hot water, working at heights, hazards of working with acid, see MSDS, working safely on top of the cooling tower, confined space entry, water basin empty, equipment failures, corrosion and wood decay. The equipment found in a cooling tower system includes: centrifugal pump 302 is a vertically mounted centrifugal pump designed to operate at 525 GPM at 85 degrees Fahrenheit or 29.44 degrees Celsius at 50 psi-G. Heat exchanger 204 is a horizontally mounted, shell-end tube, multi-pass heat exchanger designed to condense vaporized butane into the liquid state. The pressure is 115 psi-G on the shell side and 50 psi-G on the tube side. The tube side contains cooling water from the cooling tower system. The shell side contains vapor or liquid butane at 115 psi-G. The heat exchanger is comprised of stainless steel and is rated at 225 psig at 250 degrees Fahrenheit or 121.11 degrees Celsius on the tubes and 225 psig at 300 degrees Fahrenheit or 148.88 degrees Celsius on the shell. The inlet pressure on the tube side is run at 50 psig and 45 psig on the tube outlet. The tube delta pressure is 5 psig. Cooling tower fan is mounted on the top of the water distribution pipe in the center of the cooling tower. A local controller and on-off switch are located near the motor. The motor is designed to run at 250 RPM and can be adjusted depending upon need. Plenum is the open area directly under the fan. In an induced draft, cross-flow cooling tower, the velocity of the air creates a partial vacuum under the fan as it expels the vapor-enriched air. Water distribution system consists of a 12-inch deep pan, 4 feet 3 inches 20 foot, with holes equipped with stationary spiral nozzles that distribute the water across the fill. A pan with holes and nozzles is located on the east and west side of the cooling tower. Water basin is a concrete reinforced structure designed to store water and provide a foundation upon which the rest of the cooling tower can be supported. The basin is designed to collect the water as it flows across the horizontal fill and downward. The water basin provides suction for the water pump and must be able to resist chemical attack. Technicians working on the cooling tower basin must place careful attention to water pH, temperature, parts per million, and biological problems. Basin heaters come in a variety of designs: low-pressure steam, electric, or hot oil. The primary purpose of a basin heater is to keep the cooling tower clear of ice during the cold winter months. Louvers are evenly spaced and designed to direct airflow across the downward flow of water. Fill provides a vastly expanded surface area interface that enhances air-liquid contact. As evaporation occurs, the air becomes saturated with water and is carried out of the cooling tower system. The fill is comprised of pressure-treated materials, wooden slates, run through a plastic support structure. The fill is designed to provide plenty of surface area so good air-liquid contact is ensured. Evaporation takes place inside the fill area, transferring heat energy to the moist area, increasing the relative humidity in this area to 100%, and moving this heated plume into the atmosphere. The plume or fog is virtually harmless except that it can reduce visibility when it touches the ground. Evaporation accounts for 80 to 90% of the heat transfer in a cooling tower. This convective process takes place as the hot water cascades down the fill or splash boards. As the hot water spreads out across the fill, air flows over the area. This picture illustrates how the rising hot water vapor or heat energy is carried out of the cooling tower and the cooler water drops down into the water basin. Drift eliminators block and prevent water loss from the system. As hot, moisture-rich vapor flows across the fill, it is lighter than the outside air and accelerates as it enters the plenum. This warm air increases in velocity as it is propelled high above the cooling tower by the fan. Blowdown draw-off or blowdown is primarily used to control the buildup or concentration of minerals in the recirculation water. The blowdown system is designed to control the level of suspended solids in the water basin. High levels of suspended solids will cause fouling. Blowdown is closely related to the term concentration cycles. Blowdown refers to automatically removing 7 to 10% of the water in the water basin and replacing it with fresh water. In most cases, the water makeup system runs continuously due to evaporative losses and drift losses, and draw-off. Concentration cycles in the cooling tower typically can range from 3 to 7. The cooling tower is typically set at 6 concentration cycles before it blows down the system. A cycle describes one pass from the cooling tower to the process and back to the cooling tower. Cycles of concentration display the accumulation of dissolved minerals in the recirculation system. Cell is the smallest subdivision of a cooling tower that can function as an independent unit. pH control is an automatic control system, continually analyzes the pH in the basin and adds small amounts of acid or caustic to maintain operational requirements. Water treatment is the composition of the chemicals used in the water treatment system is designed to control scale, algae, corrosion, wood decay, and to help suspended solids to precipitate out in the basin. Basin level control is water level in the basin is controlled as a level element, and transmitter sends a signal to a controller. Analytical control features on the cooling tower. System pH Control, AIC 300 Analytical Indicating Controller. The purpose of this controller is to control the pH inside the cooling water basin. The pH in the cold water basin has a tendency to increase in alkalinity. The control set point is 7.8 pH. AIC 300 continually analyzes the pH in the basin and adds small amounts of acid to maintain operational requirements. The cooling tower specification range is 7.6 pH to 8.4 pH on water in the recirculation system. This picture shows a pH scale. Blowdown Control, AIC 301 Analytical Indicating Controller. The purpose of this controller is to monitor and control the levels of suspended solids. Using either draw-off or blowdown, this process is primarily used to control the buildup or concentration of minerals in the recirculation water. The blowdown system is designed to control the level of suspended solids in the water basin. High levels of suspended solids will cause fouling. Blowdown is closely related to the term concentration cycles. Blowdown refers to automatically removing 7 to 10% of the water in the water basin and replacing it with fresh water. In most cases, the water makeup system runs continuously due to evaporative losses, drift losses, and draw-off. The concentration cycles in CTW 302 range is set at 6 concentration cycles before it blows down the system. A cycle describes one pass from the cooling tower to the process and back to the cooling tower. Cycles of concentration display the accumulation of dissolved minerals in the recirculation system. Suspended Solid Chemical Control, AIC 302 Analytical Indicating Controller. The purpose of this controller is to control scale, algae, corrosion, wood decay, and to help suspended solids to precipitate out in the basin. AIC 302 monitors conditions in the basin and maintains unit specifications by adding liquid chemical treatment. Liquid treatment is set at 4.5. Fan Speed and Temperature Control, SIC 300 Speed Indicating Controller. The speed on the fan is set at 250 RPM and can be adjusted by the technician. An on-off switch is also located near the motor. Common cooling tower problems and solutions. Cooling towers can be shut down easily, however, unless a serious problem occurs or equipment repair and turnaround are scheduled, the tower is kept in continuous operation. There are some common problems and concerns for which the cooling tower system must be monitored. Cooling tower efficiency, wet bulb temperature and humidity cooling. Since wet cooling towers respond to evaporation, relative humidity has an effect on the efficiency of cooling tower system. Wet bulb temperature is taken using a specially designed thermometer and wick arrangement. In multi-cell operations, additional fans are typically applied. However, since CTW 302 has a single fan, the RPMs can be increased to improve airflow through the cooling tower. Higher temperatures will also affect the ability of the cooling tower to expel heat. pH problems. Process technicians use pH to express alkalinity or acidity. The pH scale has number values from 0 to 7 to 14. A pH reading of 7 is classified as neutral on the pH scale. As the indicator needle begins to decrease below 7, it moves into the acidic range. Readings above 7 are classified as alkaline or caustic. Examples of an acid include lemon juice, sulfuric acid, and hydrochloric acid. Examples of an alkaline include ammonia, soap, bleach, and drain cleaner. Scale formation. Scale is composed of dissolved minerals such as calcium and magnesium. Scale buildup is a process where concentrated minerals form a solid coating on the inside of piping and tubes, reducing fluid flow and heat transfer. Cooling tower water that has a high pH tends to enhance scale formation. Sulfuric acid is used to decrease the pH in the catch basin. Total dissolved solids, TDS. Water naturally contains magnesium and calcium in the form of dissolved solids. As water evaporates out of the cooling tower, dissolved minerals are left behind and, over time, concentrate and form scale. Dissolved solids break down the components and wood fibers that provide support for the cooling tower's internal structure. Sulfuric acid can minimize problems caused by dissolved solids. Blowdown on CTW302 is timed so chemical injection has time to blend into the recirculation system. A chemical additive is added in a section of the cooling tower where turbulent flow enhances mixing and where it is not drawn into pump 302 suction before adequate blending has occurred. Microorganisms, chlorine and bromine concentrations. Cooling towers provide the perfect breeding ground for microorganisms since they are exposed to warm water and sunlight. Microorganisms form slime that can build up and restrict water flow and conductive heat transfer. Biocides such as chlorine and bromine can control the growth of these organisms. Unfortunately, chlorine is an extremely hazardous material and must be handled with caution. Bromine is a little safer to handle and use. CTW302 utilizes a special blend of biocides to keep the cooling tower operating smoothly. Other chemical inhibitors are added to this blend and need to be thoroughly mixed with basin water. Dissolved gases. Cooling tower water may have dissolved gases like oxygen, hydrogen sulfide, and carbon dioxide that chemically react with iron. These gases will enhance corrosion, destroy metal surfaces, damage valuable equipment, and deteriorate metal pipes, brackets, and bolts used to secure wood products together. High quantities of dissolved gases will make the catch basin water acidic. Ruptured heat exchanger tubes. If the tube ruptures on X2O4, the butane, pentane, and catalyst mix will pour into the recirculation water since it is at 100 psig and the recirculation water is at 45 to 50 psig. The pH of the cooling tower water would also become very alkaline and set off the high pH alarm. Fan 300 failure. CTW302 operates the fan when temperatures and relative humidity reach predetermined levels. During the winter months, the fan is rarely operated and the hot water bypass system is frequently used. A spare motor, gearbox, and fan blade arrangement are located in the maintenance shop. Several days, however, are typically required for large projects. It is possible to operate the cooling tower in a natural draft condition. Pump 302 failure. If pump 302 fails, the distillation system will immediately go into alarm condition. The pump backup system will need to be placed online immediately. P302 is a vertically mounted centrifugal pump with a series of small screens installed on the suction side of the pump. These screens keep the liquid entering the pump clean and prevent internal damage. NPSH, net positive suction head, and NPDH, net positive discharge head, must be kept between specific specifications in order for the recirculation system to operate properly. Instrument problems. Instruments on the cooling tower include 3 analytical control loops, 1 level control loop, 2 temperature control loops, and 1 speed control loop on the fan. A variety of simple instruments are mounted on the cooling tower system. Suspended solids, X2O4 tube fouling. As air circulates through the cooling tower, it carries solids in the form of small dust particles. These solids are captured by the downward flow of water and collected in the catch basin where they form sludge. Sludge is removed through the blowdown system. Suspended solids can build up inside the tubes of a heat exchanger and cause fouling. Fouling is a term used to describe restriction or plugging. Blowdown and cycles of concentration problems. Concentration cycles in cooling towers range from 3 to 7 and are dependent upon the quality of the makeup water. Circulating water in CTW302 is filtered and treated with biocides and algicides to prevent microorganism growth and a control system for pH adjustment. Broken or collapsed fill. High winds, ice buildup, corrosion, microorganisms, and other variables can cause structural damage to the cooling tower. While a cooling tower is a simple design, it needs all of its parts to operate efficiently. Fill or splashboards can be replaced and put back in place. Bolts and brackets that have been corroded need to be repaired. Water distribution system problems. The water distribution system has a variety of components including a series of valves, pans, water distributors, and pan covers that can be damaged. Pipe leaks are not uncommon and can quickly lead to larger problems. If the water distributors become dislodged from the pan, uneven amounts of water can flow over the fill before it has time to contact air flowing through the tower. Simple startup procedure for cooling tower system. 1. Notify your supervisor and all concerned about startup. Downstream process technicians, I&E, engineering, maintenance, etc. 2. Ensure all safety hazards are secured. Trash, locks, old permits, etc. 3. Check equipment and instrumentation. Stroke control valves 0 to 100%, check lineups, etc. 4. Establish level in water basin and set LIC 300 at 75% and place system in auto. 5. Sample water in basin and send to lab. 6. Line up pump 302 from basin to pump to exchanger 204 to cooling tower 302 water distribution system. 7. Line up EX 204. 8. Start pump 302 and monitor Pi 300A 50/50 PSIG and Pi 300B 45 PSIG. 9. Set FIC 300 TO 525 RPM and place in auto. 10. Start fan 300 and set SIC 300 to 1250 RPM. 11. Set AIC 300 to 7.8 pH and place in auto. 12. Set AIC 301 to 30 ppm and put in auto. 13. Set AIC 302 to 4.5 GPH and place controller in auto. 14. Set TIC 301 to 125 degrees Fahrenheit and put in auto. 15. Set TIC 302, low pressure steam, to 60 degrees Fahrenheit and put in auto. 16. Record T300A wet bulb temperature, WBT. 17. Record T300B. 18. Calculate the approach to the tower. 19. Carefully monitor all conditions and collect makeup water sample, basin samples, and P302 discharge. 20. Verify all process variables with standard operating procedure. Cooling tower symbols. Each type of cooling tower can be represented by a symbol. This picture illustrates cooling tower symbols. A cooling tower is a heat transfer device used by industry to cool hot water for reuse in process systems by evaporation and sensible heat loss. Hot water transfers heat to air as it passes in the tower. Evaporation accounts for 80 to 90% of the heat transfer in a cooling tower. Cooling tower efficiency is affected by relative humidity, temperature, wind velocity, tower design, water contamination, and equipment problems. Cooling towers are classified by how they produce airflow and the direction the airflow takes in relation to the downward flow of water. Atmospheric towers use wind to move air into and out of the tower. Their efficiency depends on wind velocity. Hyperbolic or chimney towers are natural draft towers that produce airflow by temperature-induced density differences. Forced draft cooling towers produce airflow mechanically through the use of fans located on the lower side of the tower. The fans push air into the tower. Induced draft towers have a fan on top of the tower. The fan pulls hot air out of the top of the tower. Water cooling systems use heat exchangers and cooling towers in combination. Cool water is pumped from the tower to a heat exchanger, where hot process fluid transfers heat to the cool water. The hot water is returned to the tower to be cooled. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.